Hi everyone. Today's lecture is about two more advanced controllers. One is ratio controller. Okay, ratio controller. Okay, ratio. This one right here. Ratio control. Okay. So what is ratio controller? It is a special type of feed forward control. It's not a feedback controller because we are not going to take action once the disturbance affected the process. We are going to take action before the disturbance affect the process. So it is a special type of feed forward controller where two disturbances are measured because it is a ratio. So we need two elements to maintain the ratio. So it is a special type of feed forward controller where two disturbances are measured and held in a constant ratio between the two disturbances. So here we have to measure the two disturbances and we have to maintain the ratio. So that is called as ratio controller. It is commonly applied. It is mostly used in the industry to control the ratio of flow rates of two different streams. Okay, but the condition is both flow rates should be measured. Okay, both flow rates should be measured, but only one should be controlled. So this is the condition. So ratio control is a special type of feed forward controller in which two disturbances are measured. Only one disturbance is to be controlled, measured and controlled. The other disturbance should not be under control. So the disturbance which is not under control is called as wild stream. Okay, so we have to pick which one is a wild stream, which one is a controllable stream. So we have to take two flow rates. So one should be controlled stream, another one is wild stream. So we have to measure this is the distance. So you have to measure the disturbance. So measure the flow rate, and then this also measure the flow rate. So this is FA and FB. Then divide this. So it will be FA by FB. So this is the measure ratio. So you already have, suppose this FA by FB may be 0.6 and then the desired ratio is 2. So that 2 is compared with 0.6, then accordingly it takes an action. So GR is a normal conventional controller. So you can use PID. So based on the error, it will generate the control action. Then that control action will be implemented on the controller. So accordingly, uh, the flow rate may be varied. So when the flow rate varies, then FB varies. Then accordingly, your ratio is moving towards the desired ratio. So this is how it works. So we can do or we can implement ratio controller in two methods. One method is measure the two disturbances and maintain a ratio, and then one should be wild, another one should be controllable. Then apply that control action on the controllable stream. So this is one case. Okay. In the next cases, for example, if you maintain the ratio as FB by A because flow rate of B and flow rate of A stream is equal to 3 by 2 means, so now I'm going to take FB equal to 3 by 2 into FA. So what I'll do is I will keep this as the variable now. Okay, instead of ratio, I'm going to consider that ratio should be multiplied by the flow rate and I have some value for this. So instead of ratio, if I control this FB, then that becomes a ratio control. So how do we do that? So here the one which is not under mesh controlled is wild stream. So that is FA, so that FA is measured over here, and then this here ratio is 3 by 2. Then this becomes 3 by 2 into FA. Okay, so that is compared with FB. So this is compared with the FB. So this is the desired one. This is the desired one because the ratio is here, and this is the measurable one. If there is any issue, then that error is given to a controller. Then accordingly, it will change the flow rate. Okay, so we are driving this flow rate towards 3 by 2 FA. So this is one more logic, one more methodology. So this is how your ratio control works. So ratio controller is a special type of feed forward controller. In this case, we measure two disturbances and we have to maintain the ratio in one case. In other case, we just allow that ratio should be multiplied by the known flow rate. Then you have to take that as a set point. Then you have to measure this. So drive FB so that it will reach 3 by 2 FA. For that you need this controller. This controller is always a conventional controller, PPI, PD, PID, like that. So in this way we can apply ratio controller methodology. So example is, if you want to keep a constant ratio between the feed flow rate and the steam in reboiler and distillation column, that is one thing, one example. Then if you want to control the ratio of two reactants entering a reactor at a desired valve, that's also one more example. And then keep the ratio of fuel versus air, fuel versus air. Okay, so which is, we know that that is 4:1 ratio, that for combustion. So keep the ratio of fuel with respect to air in a burner, okay, for the optimum value. And we can hold the ratio of two blended streams constant in order to maintain the composition of the blend at desired value. So these are the examples. So this is about ratio controller. So next one is inferential controller. Inferential controller. So why it has got the name inferential? Because if your output is unmeasured, okay, so if your output is unmeasured, in that case you have to infer the unmeasured output from the measured output. So that is called as inferential. So once again I'll repeat. So inferential controller means, just say for example, you have unmeasured output. The output is unmeasured, okay? But I have to control this. So how do I control? I have to control this unmeasured output with the measured output, some other output. So I'm going to control with the inference of this. So that is why it has got the name inferential controller, okay? So far, none of the control configurations studied so far can be used to control unmeasured process output, okay, in the presence of unmeasured disturbances. So here we can see unmeasured disturbances. So this is this control output, but which is unmeasured. But this is a secondary measurement which is measured. Okay. So far, none of the control configurations address the issue of control of unmeasured output in the presence of unmeasured disturbances. So for this, inference control is the only way to deal with this. Okay. So let us do that with one simple derivation. So let us write the equation for this block diagram. So what is controlled output? Sorry, control output, but which is unmeasured. So y is equal to, so this is value m, so gp1. So m into gp1 plus d into GD1. So this is 1. Okay. Similarly, for the known one, secondary measurement. So it is M into GP2 plus GD D into GD2. So this is 2. Okay. So we know this is the measurement. So from this, we take one value and substitute here. This is the logic. So how do we do that? So we need D, because I'm going to substitute D over here. So for that, dGD2 is equivalent to Sz minus M GP2. I want only D. So D is equal to Z by GD2 minus M GP2 minus GD2. Okay. So next we have to substitute D in 1. Okay, because I have to infer. So I'm going to infer from Z, and I have to substitute that value in this case. Okay. So what is Y now? So Y is equal to M GP1 plus, in the place of this, substitute here. So GZ by GD2, so already you have GD1 minus GP2, then GD1 by GD2, which is M. Okay. Next, so from this, Y equal to GP1 minus GD1, here GP1 minus GD1 by GD2 into GP2. This is M, and another term is Z. Z into GD1 by GD2, because we have combined that. Okay. So now this is your unmeasured output, but it has a value. So how it has a value? Because we inferred from the Z1. Okay. So Z is known. We know the transfer function of the disturbance 1. We know the transfer function of GD2. and we know the transfer function GD1, GD2, we know the transfer function of GP2, we know the transfer function of GP1. So when you combine all this, then you will get a value for Y. Okay, so this is one special one. So what is the case? That is, if your output is unmeasured, then we have to give a value for that unmeasured output that has to be inferred from the known measurement. So the known measurement is Z. Okay, so just we implement that in this block diagram. So this is your process. From the process only, Y is unmeasured and then Z is measured. Okay, that Z should be multiplied by GD1. So GD1 by G2, that is added with. So here we have a summer. In that summer, you have M. This M is from the controller. Okay, so this is M. Okay, so what is M? GP1 minus GD1 by GD2, GP2. Okay, so this is M. So this is added to this. So here this is the estimate of the unmeasured output. So this becomes Y now. So see what is Y now. So Y1 is this term, this multiplied by this, and then this added with this. So this is the estimate of this Y, and then that is Y is given to this. Okay, this is estimation. This is the original one set point. Then if there is any difference, then that error is given to the controller. Then accordingly the controller will change the value, because we cannot change this transfer function, but it will change the actuation. So accordingly it varies. So again, the estimation value is changed. So you are going to drive this estimation to reach your set point. So this is how it works. So inferential controller is one important controller, because the disturbances are unmeasured, and the control output is also unmeasured. So we have to give a value, or we have to estimate the unmeasured one from the measured one, which is secondary measurement. That is why it has got the name inferential. This is one example. You can try it in MATLAB. Okay, so this is GD1, GD2 is known to you. GP1, GP2 is also known to you. This is the unmeasured one. So this overhead composition means this is your distillation column. So in distillation column, this is called as overhead. Okay, in the overhead composition. So this is the overhead composition. Then this is the first tray. You have many trays. This is the tray. So this temperature is, we know this temperature because temperature is measurable. We have devices like thermocouple. So we will understand the measurement of the, we know the temperature measurement using this. But there is no sensor to measure the overhead composition. So I have to estimate it. So how do I estimate it? With the known value, with the known temperature value. So if you substitute in the required equation, so you will get this, and you can try this controller. From this you can find out the estimate, and you have to tune the controller in such a way that this estimation is reaching the YSP. So this is how it works. So far we have discussed 5 different controllers. One is cascade, next one is split range, next one is feed forward, next one is ratio, and the next one is inferential. Okay, in this cascade is more than one measurement and one manipulated variable. This is one measurement and more than one manipulated variable. FF does not belong to normal PID controller. It is a machine computer, I can say. FF is a computing device which computes the control output. Ratio is you have to maintain the ratio. Inferential is you have to estimate the variable to be controlled from the known measurement, because known measure means we can't say that all the variables are not provided with the sensors. There are variables like temperature, flow, pressure. We have sensors to measure it. From that we can infer the unmeasured or unmeasured output. So this is how it works. So thanks for watching. That's all for today. Thank you.